handling and steering that are responsive and free from wander or pull. A ride that's free from annoying vibration or noise. These are qualities customers expect from their Jeep Eagle vehicles. So, when a customer's vehicle doesn't handle or ride the way it was designed to, it's your job to find the cause. In other words, when it comes to achieving customer satisfaction, a knowledge of wheels, tires, and suspension systems is essential. In this program, we're going to cover the basic information you'll need to resolve customer complaints in these areas, including tire design, ratings, and required maintenance, and tire and wheel problem diagnosis and correction. Then we'll review the different types of suspension systems and the basic alignment angles and their effect on handling and steering. Finally, we'll examine procedures you need to be aware of when performing an alignment. Let's begin with a look at some tire basics. Although their appearance and size may vary considerably from vehicle to vehicle, most tires are similar in the way they're put together. A bundle of wires called a bead provides strength where the tire meets the wheel. The body plies, consisting of tire cords and rubber, curve around one bead, across the tire, and around the other bead. Because this is a radial tire, the body plies are perpendicular to the direction of travel. Between the body plies and tire tread are stabilizing belts, again consisting of tire cords and rubber. The belts help support the tire and keep the tread open for greater traction. The tire sidewalls and tire tread are made of a mixture of natural rubber and synthetic rubber. The tire parts are bonded to one another using heat and pressure in a process called vulcanizing. Because of their superior performance, radial tires are used exclusively as original equipment on passenger vehicles. As mentioned earlier, on a radial tire, body plies run at a right angle to the direction of travel. This design results in less internal stress during turning and lower friction when rolling. This is why radial tires provide better fuel economy and greater steering sensitivity. You can find out a lot more than the tire design by learning to read the sidewall of a tire. Let's start with the tire size. Most of the tires you'll encounter will have a metric size description. The metric classification is replacing the alphanumeric designation in which a letter provided load information. Let's examine exactly what the metric size rating stands for on a P205 60R15 tire. The P at the beginning of the designation specifies the application, passenger car. The number following the application is the width of the tire cross-section in millimeters when the tire is mounted on a rim. The next number is the aspect ratio, the ratio of the tire's height to its width. An optional letter after the aspect ratio specifies the speed rating of the tire. The R indicates that the tire is a radial, and the 15 indicates the wheel size. An arrow on the sidewall of the tire indicates that the tire is unidirectional, designed to rotate in one direction. When replacing tires on a vehicle, it's important to use the same size and type of tire as a replacement. Mixing radial and non-radial tires, for example, will affect handling and steering response. Changing tire sizes will alter the relationship between vehicle speed sensor signals and actual vehicle speed. Changing tire sizes can also affect the inputs to the controller for anti-lock brake operation. On four-wheel drive vehicles, changing tire sizes can result in damage to driveline components. On the sidewall of a tire, you'll also find the uniform tire quality ratings for tread life, traction, and heat resistance. These ratings are arrived at by the U.S. government to give consumers a way to compare tires. tread life rating as a percentage which represents the tire's amount of tread life in comparison to a reference value of 100. For example, the tread on a tire rated 280 could be expected to last 2.8 times longer than tread rated 100. The traction and heat resistance ratings are indicated by a letter grade, A, B, or C, with A being the highest. Some tires may also have a letter designating the load range. This letter replaces the ply rating used previously. And all-season tires have M and S in some combination to indicate that they are designed to operate in mud and snow. Of vehicle components which require routine checking and maintenance, tires are one of the most likely to be ignored. Yet inflation pressure, for example, can have a dramatic effect on tire life, on the way a vehicle steers and handles, and on fuel economy. Keep the following items in mind when checking inflation pressure. Do not bleed off air from a hot tire to bring inflation pressure to within specifications. A pressure reading on a hot tire is not accurate. Check inflation pressure with the tires cold. The vehicle should not have been driven for at least 3 hours. Finally, follow the recommendations on the tire inflation placard or in the owner's manual. Keep in mind that inflation pressure recommendations do not apply to compact spare tires, and compact and lightweight spares are limited in both tread life and in the speed they can be driven. Tire rotation is another aspect of tire service that is often ignored and an area that is surrounded by a great deal of confusion. Tire rotation can help equalize tread wear and greatly extend tire life. Rotation can be particularly important on front-wheel drive vehicles. Because of the difference in the amount of tire-to-road contact between the front and rear of these vehicles, irregular wear can develop in rear tires which are not rotated. The rotation pattern depends on whether a vehicle is front-wheel drive, rear-wheel drive, or four-wheel drive, and whether the vehicle uses unidirectional or non-directional tires. The basic patterns to keep in mind are the front cross for front-wheel drive vehicles with non-directional tires, the rear cross for rear-wheel drive vehicles with non-directional tires, and same side rotation for vehicles with unidirectional tires. Four-wheel drive vehicles with non-directional tires use a cross rotation pattern. Now that we've gone over tire and wheel basics, next we'll look at some procedures to use for problems that could be tire or wheel related. Because of the variety of symptoms and the wide range of possible causes, diagnosing a noise or vibration complaint can be difficult. It's important, therefore, to use a systematic approach that covers all the bases. Part of this approach is a thorough preliminary inspection. Be sure to check drive shafts and yokes for incorrect angles and U-joints for wear or damage. Check for loose or worn steering or suspension components, a loose rack and pinion assembly, or loose wheel bearings, loose wheel nuts, or an improperly mounted wheel. When inspecting the wheel, look for damage or evidence of missing wheel weights. Always check the inside of wheels for dried mud or other foreign matter that may affect wheel balance. The tire bead should be properly seated on the rim, and tire inflation pressure should be within specifications. Check tire tread for distortion and wear. Tires which are worn down to the tread wear indicator bars should be replaced, as should tires which are worn unevenly. When road testing a vehicle, try to isolate the cause of the vibration or noise according to the conditions under which it occurs. For example, does the vibration occur in a particular range of vehicle or engine speed? Is the vibration torque sensitive? For example, could it be related to engine or transmission mounts? Does the noise disappear during neutral coast down? Is it driveline related? Does the noise or vibration increase or decrease during braking? Does the noise or vibration occur only on turns? Is it CV joint or wheel bearing related? For general noise and vibration diagnosis, it's a good idea to use a log sheet to record the results of the road test. Comparing your results to a diagnosis chart should give you a pretty good idea of where to concentrate your troubleshooting. If the noise or vibration was related to vehicle speed and was not affected by a neutral coast or turning or braking, there's a good possibility that it's wheel or tire related. Before we discuss some common wheel and tire conditions, we need to discuss what occurs when a tire is not perfectly true or when its weight is not distributed equally. When a disproportionate amount of weight is concentrated in a small area of a tire or wheel assembly relative to the axis of the tire and wheel, the heavy spot exerts up and down force as the tire rotates. This is known as static imbalance and results in an up and down movement in the tire and wheel. When a disproportionate amount of weight is concentrated in a small area relative to the tire plane, the heavy spot exerts side-to-side force as the tire rotates. This is known as dynamic imbalance and results in side-to-side movement of the tire and wheel. In addition to heavy spots, dimensional irregularities or runout can cause tire and wheel problems if it is excessive. Radial runout occurs when the tire and wheel assembly is not perfectly round. Lateral runout occurs when the tire and wheel assembly is not symmetrical from side to side. Excessive radial and lateral runout can cause conditions similar to those caused by static and dynamic imbalance. Now, let's look at some tire and wheel conditions which may result from imbalance or excessive runout. Tire waddle is side-to-side motion that occurs at low speeds. A slight amount of waddle may be normal in a radial tire, but excessive waddle may be the result of lateral runout. Another complaint is tire thump, a repetitive noise that occurs with each tire rotation. Thump usually disappears when the tire is warmed up. Tire tramp or wheel hop is a vibration caused by a tire and wheel moving up and down during rotation. The vibration is most noticeable in the 20 to 40 mile per hour range. In addition to static imbalance, wheel hop can be caused by excessive radial runout. Wheel shimmy is a speed-sensitive vibration that occurs at medium to high vehicle speeds. It's caused by side-to-side shaking or vibration of the tire and wheel. In addition to dynamic imbalance, shimmy can be caused by extreme lateral runout. Shimmy can also be caused by loose wheel bearings or by worn or loose steering components. For a detailed procedure for tracking down the cause of wheel shimmy on Jeep vehicles, see the front suspension section of the Jeep engine, chassis, and body service manual. When you believe a noise or vibration is tire and wheel related, the first step is to check tire and wheel assembly radial and lateral runout on the vehicle. You can determine radial runout by setting the dial indicator to 0 on the lowest part of the tire and then rotating the tire. Record the highest reading. For lateral runout, 0 the dial indicator on the lowest spot on the tire's sidewall as close to the tread as possible. Then rotate the tire to find the maximum reading. When an on-vehicle check shows that excessive runout is the cause of vibration, you can continue diagnosis by checking radial and lateral runout off the vehicle. This will tell you whether the problem is in the wheel and tire assembly or the hub assembly. After marking the wheel location relative to the wheel studs, remove the wheel and tire from the vehicle and install the assembly on a properly calibrated wheel balance machine. Determine radial or lateral runout as described earlier and mark the spot on the tire. Also, make a corresponding mark on the wheel. To see if radial or lateral runout is excessive, compare the readings to the specifications in the service manual. If the runout is within specifications, the problem is in the hub assembly, and you'll need to check runout on these components. But if the runout is excessive, you can use a tire-to-wheel match mounting procedure to reduce runout. This procedure is explained in Technical Service Bulletin 220189. After marking the location of the tire relative to the valve stem, break the tire loose and rotate it 180 degrees on the wheel. Then, recheck runout. If runout still exceeds specifications, mark the high spot on the tire. If the new high spot is within 4 inches of the original high spot mark on the tire is at fault and should be replaced. If the new high spot is within 4 inches of the original high spot mark on the wheel, you'll need to check the wheel for excessive runout. If the new high spot is not within 4 inches of the original high spot mark on the tire or the wheel, draw an arrow from the second high spot to the first high spot in the direction of the shortest distance. Rotate the tire 90 degrees on the wheel in the same direction as the arrow. This will normally bring runout within specifications. When reinstalling the tire and wheel on the vehicle, be sure to use the reference marks on the wheel and wheel stud to return the wheel to its original position on the vehicle. If the vibration persists during the road test, you may need to rotate the tire and wheel on the hub to minimize runout from the hub assembly. The next step in eliminating vehicle speed-sensitive vibration is to perform an off-the-car dynamic balance of wheel and tire assemblies. Later model dynamic balance machines do everything but put the weights on for you. But there are a few items to keep in mind during dynamic balancing. Always mark the position of the wheel relative to the wheel studs so the assemblies can be reinstalled in the same position. Check the wheel balancer calibration at least once every 2 weeks. Always place the back of the wheel against the proper size cone. This ensures an accurate mounting. Tighten the wing nuts securely against the wheel. Otherwise, the machine's weight location indication may be incorrect. If you have to add more than 3 ounces of weight to any location, you may have to rotate the tire on the wheel to reduce the amount of weight needed. After adding weight, always re-spin the tire and wheel assembly to make sure the weights are correct, and road test the vehicle to check for vibration. If off-car balancing failed to remedy the condition, you'll need to use an on-car balancer to correct for imbalance in the hub, rotor, drum, or wheel cover. If you do perform an on-car balance, be sure to inform the customer that the tires and wheels must be rebalanced if they're moved from their location on the vehicle. Besides noise and vibration, occasionally tire irregularities can cause a tire lead or pull condition. When a vehicle pulls to one side, tire lead should be eliminated as a cause prior to alignment procedures. The reference book accompanying this program contains a chart for diagnosing and correcting tire lead. Now that we've covered tires and wheels, let's move on to suspension, starting with a look at the types of suspensions you're likely to encounter. Among the variety of front suspension designs in use today, the most common type for passenger cars is McPherson struts. In fact, you'll find some variation of McPherson strut suspension on all domestic and imported front-wheel drive Jeep Eagle vehicles. Because of this, we need to examine strut-type suspension in some detail. Struts, which incorporate a coil spring and shock absorber, are attached at the top to the upper fender reinforcement and at the bottom to a steering knuckle. The upper strut assembly has a pivot bearing which allows the strut to turn with the steering knuckle. A ball joint connects the bottom of the steering knuckle to a lower control arm. The control arm is connected to the vehicle's front crossmember. Pivot bushings allow the control arm to move up and down relative to the crossmember. The strut coil springs hold the vehicle at its ride height as the tires move over irregularities in the road. The strut shock absorbers dampen spring movement. A stabilizer bar transfers some of the load from one side of the vehicle to the other to minimize body sway. Other front suspension designs use coil springs and separate shock absorbers. Jeep MJ and XJ models use a coil spring between the body and axle along with locating arms. This design, known as Quadralink, also uses a track bar to control lateral motion and a stabilizer bar to control body sway. Shock absorbers dampen spring motion. Some four-wheel drive vehicles use leaf springs on the front axle. Jeep SJ and YJ models use front multi-leaf springs mounted at the front and rear to the vehicle frame. A track bar controls lateral suspension movement, while a stabilizer bar controls body sway. Rear suspensions use a number of different designs to control ride. The most common on passenger cars is the trailing arm type, with coil springs, torsion bars, or struts. Premier uses a trailing arm suspension, but instead of coil springs, 4 interconnected torsion bars run between the trailing arms and are attached to the chassis through support brackets. The torsion bar assembly also functions as a stabilizer bar to control body sway. Gas-charged shock absorbers dampen suspension movement. The Summit and Talon use struts instead of coil springs between the trailing arms and chassis. A torsion bar between the rear wheels reduces body sway during cornering, and a lateral rod controls side-to-side suspension movement. The rear suspension of the all-wheel drive Eagle Talon uses a double wishbone design. This design includes struts between the trailing arms and chassis and control arms between the differential and trailing arm. A stabilizer bar is attached to the trailing arm to reduce body sway. Instead of coils or struts on trailing arms, some vehicles use leaf springs attached to the chassis for their rear suspensions. Jeep SJ and YJ models use leaf springs with a track bar to control lateral movement and shock absorbers to dampen spring motion. MJ rear suspension also uses leaf springs and shock absorbers, while XJ models add a stabilizer bar to control body sway. The reference book accompanying this program contains a chart listing the different types of front and rear suspensions according to model. No matter what type of suspension a vehicle is equipped with, suspension service involves a check of the orientation of the tires and wheels with respect to the rest of the vehicle. Alignment angles. The basic alignment angles are the subject of the next part of this program. The purpose of alignment angles in suspension design is to allow the tires to track straight when the vehicle is in motion, to provide optimum high and low speed handling and steering response, and to minimize body sway during cornering and tire wear. An understanding of the adjustable and non-adjustable alignment angles, including their effect on handling and tire wear, is crucial in suspension service. Angles which are non-adjustable can still provide an indication whether a suspension component is worn or damaged. Let's begin our discussion with camber, caster, and toe, 3 alignment angles which are adjustable on many vehicles. Camber is simply the inward or outward tilt of the wheel and tire relative to the chassis. When the tilt at the top is inward, camber is negative. Outward, camber is positive. The amount of tilt is measured in degrees. You may be wondering why tires and wheels aren't simply fixed at 0 degrees camber. The fact is that while camber is adjusted with the vehicle at rest and unloaded, camber changes when the vehicle is loaded and in motion. So a slightly positive camber setting will change to 0 degrees camber when the vehicle is driven. When camber is not within specifications, tires can wear unevenly. Excessive positive camber can cause accelerated wear on the outside edge of tires. Excessive negative camber can cause accelerated wear on the inside edge of tires. Camber that is not within specifications will also cause a pull in the direction of the wheel and tire with the most positive camber. Caster is the tilt of the steering axis toward the front or rear of the vehicle. On a McPherson strut suspension, the steering axis is a line drawn through the strut upper mounting and control arm ball joint. Caster is positive if the axis is inclined to the rear and negative if the axis is inclined forward. Like camber, caster is measured in degrees. If caster is not equal, a vehicle will tend to pull in the direction of the side with the least positive caster. But caster that is out of specifications does not accelerate tire wear. Caster has a number of important effects on steering, handling, and tracking. Positive caster causes the steering axis to lead or pull the tire and wheel down the road. As a result, positive caster resists changes in direction and aids in directional stability. At the same time, positive caster increases the amount of steering effort, but this can be offset by steering axis inclination, as we shall see. Negative caster can aid in directional stability, but in a different way. A tire and wheel with negative caster will tend to steer into side forces such as those caused by wind. On turns, positive caster increases negative camber on the outside wheel and positive camber on the inside wheel. This counteracts body sway and improves handling. One other effect of positive caster is that it increases the wheel's tendency to toe in when the vehicle is moving. Negative caster increases the tendency to toe out. Our next alignment angle, toe, is simply the difference in the distance between the front and rear of a set of tires. When the front edge of the tires are closer together, the tires are toed in, also referred to as positive toe. When the rear edges are closer, the tires are toed out, also referred to as negative toe. Toe can be specified in inches or degrees. As with camber, toe is often set in or out to compensate for toe-in or toe-out tendencies when a vehicle is moving. A slight amount of toe-in is usually preferred on front tires. Of all the alignment angles, toe has the greatest effect on tire wear. On radial tires, excessive toe can produce irregular wear, especially on tire edges. Incorrect toe can also cause a vehicle to wander. When a vehicle makes a turn, the toe or angle necessary to prevent tire scrub is different from that in the straight ahead position. This difference is called toe out on turns. Toe out on turns is necessary because the inside and outside wheels in a turn follow a different arc. To prevent scrub, the center line of both front wheels must meet at the center line of the rear axle. Toe out on turns is provided by the changes in geometry of the steering arms during a turn. Steering axis inclination is the inward tilt of the steering axis from true vertical as viewed from the front of the vehicle. As mentioned earlier, the steering axis on a strut suspension is a line drawn from the upper mount through the ball joint on the lower control arm. Steering axis inclination tends to push the tire and wheel down on turns, raising vehicle height. Because the vehicle weight tends to return the tires and wheels to the straight-ahead position, steering axis inclination assists steering wheel return to the center position. Steering axis inclination can be measured, but it is not adjustable. We've been looking at alignment angles with an emphasis on the front suspension, but some of the angles we've described apply to the rear wheels as well. To prevent excessive tire wear and for proper tracking and handling, all four wheels must be aligned properly. When a vehicle is properly aligned, the direction or thrust line of the rear axle should coincide with the direction or thrust line of the front axle. And both of these lines should be parallel to the vehicle center line. However, if one of the rear wheels or the axle is angled away from the vehicle center line, there is a lead in the direction opposite the thrust angle. The steering wheel must be held off-center and the vehicle dog tracks. If toe is incorrect, tire wear may result. Because of all the factors affecting wheel alignment, you can see why a thorough, systematic approach is necessary. The procedures you'll need to use in this approach are the subject of the next part of this program. With modern alignment equipment, it's easy to simply check adjustable angles, make the necessary adjustments, and send the customer on his way. But if this is all you do during wheel alignment, you may be setting yourself up for a comeback. Any alignment should include a thorough preliminary inspection and a road test. It also means checking all measurable angles, not just the adjustable ones. To see why these procedures are important, we need to look at them in greater detail. A thorough preliminary inspection includes checking the ride height of the vehicle. Ride height has an effect on camber and caster. In fact, a difference of as little as 1 inch from side to side may cause a pull. Because wheel and axle offset affect steering and handling, it's also important to check wheelbase. Checking for loose, worn, or damaged components is another essential part of a preliminary inspection. The check should include steering linkage and steering gear or rack mounting, ball joints, control arm bushings, spring shackles, stabilizer bushings, strut mounting, and strut bearing. Inspecting tires and checking out any problems indicated by tire wear is also an essential part of alignment. Don't overlook tire inflation pressure in your inspection. Incorrect pressure can cause tire wear, wander, or pull problems. When road testing the vehicle, use a flat, smooth road to avoid any lead caused by road crown and noises caused by the pavement. Differentiate between wander and lead. Causes of wander include incorrect tire pressure, incorrect toe or caster, loose steering components or wheel bearings, worn control arm bushings, excessive friction in steering components, and a misaligned rear axle. Causes of lead include unequal tire pressure, incorrect camber or caster, mismatched tires, a dragging brake, or a misaligned rear axle. As mentioned earlier, a lead can result from tire irregularities. If alignment angles are within specs, be sure to use the tire lead correction chart in investigating tire lead as a possible cause. If vibration or noise was the only symptom on the road test, it's not likely that wheel alignment is the cause, and you should concentrate on wheels and tires. Before placing a vehicle on the alignment rack, be sure to check the turn plates for free operation. Check the vehicle interior and trunk for weight, which might affect alignment readings. Jounce the vehicle front and rear to establish ride height. When checking angles and making adjustments, keep the following items in mind. For a four-wheel alignment, check and adjust rear wheels first. You can adjust rear camber and toe on all domestic front-wheel drive vehicles by using shims under the spindles. If you're doing a four-wheel alignment by backing a vehicle onto a two-wheel rack, keep in mind that toe will be reversed. Toe out will read as toe in and vice versa. When performing front-wheel alignment, be sure to check both adjustable and non-adjustable angles. By looking at settings, you can often identify a damaged component. Jeep vehicles may require alignment procedures which are different from the ones you're used to seeing on other vehicles. On MJ and XJ vehicles, to adjust toe, first center the steering wheel by counting the total number of stop-to-stop turns, then turning the wheel 1/2 that number from one of the stops. Then adjust right wheel toe to 0 using the drag link adjustment sleeve. Next, adjust left wheel toe by turning the tie rod. After adjusting toe, always position the tie rod or drag link adjustment bolts so that the bolt ends face rearward and are angled upward. On Jeep MJ, XJ, and YJ vehicles, the acceptable and preferred amounts of caster are large in comparison to that found on most vehicles. So, when checking caster on these vehicles, make sure your alignment equipment is capable of reading large caster angles. In this month's Videotech Kit, you'll find charts detailing suspension types and adjustable angles on Jeep Eagle vehicles. As we've seen, suspension service is more than balancing tires and wheels and adjusting alignment angles to specs. A professional approach requires a basic understanding of suspension design and a familiarity with the many factors that affect vehicle ride and handling. That does it for this month's program. Next month on Videotech, we'll look at changes on the 1991 1/4 Eagle Premier.